You had some things that were called amino acids: glycine, valine, proline, isoleucine. Remember, those are the building blocks, legitimately, of like proteins. So kind of big picture here. You don't. I'll tell you when to start writing. You don't need to start writing yet. This is an amino acid. The amino acids have the basic structure of this. If whatever you put here determines what type of amino acid you have, so if you change it slightly, you have a whole new amino acid. Those are the basic fundamental shapes. You can take two amino acids and link them together. So this is the typical scenario that occurs. You guys would have called this a peptide bond back in biology class. Peptide bonds are linking the primary structures of amino acids together. So you have a situation that's, as a side note, anytime in science you have the opportunity to create water, it's called a good leaving group. It's easy to remove water from a molecule. So these electrons actually take this hydrogen from here, and when it does so, or this hydrogen is rather attracted to those electrons, this bond is cleaved, and so is this bond. So what you end up having is the loss of water. So you have two hydrogens and oxygen, and then this nitrogen comes together and bonds to this carbon. So I'll just draw long bonds, but those two interact like this. And this is now officially the peptide bond. So take several of those, link them together. So carbon, I'll just shorthand it: carbon, nitrogen, right, blah, 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 carbon, nitrogen, so a whole bunch of stuff in here. Okay, so you keep getting that over and over and over again. This is the primary structure. You can take that primary structure of amino acids and contort it in three-dimensional shape, so Lewis dot structures, and you start forming what's called beta pleated sheets. Do you know other structures you can get in proteins, conformations? Beta pleated sheets. You can maybe get a turn on there, and then you might get another beta pleated sheet, and then you might get a turn, but you might get something that's in like an alpha helix sort of mentality. So proteins also have the same conformational shape that DNA would take at that moment. So primary structure, secondary structure, tertiary structure. Yeah.
Oh,
Keep going.
it's not.
Oh yeah.
It's just a
Yeah, go for it.
Oh,
Yeah.
okay. Well, if you eat something called a prion, you could seriously, mess up your whole protein structure in a way that kills you horribly.
Yeah, we do. Oh god. Oh geez. Okay. Don't eat prions. Where do we find prions? Don't know.
Sounds like Pringles.
It does. Don't eat Pringles. Start the rumor. This is it. Yeah. So primary, secondary, tertiary structure, and then take this and mix it with another one of these, and you form quaternary structure. In biology, structure determines function. You lose structure, you lose function. You lose function, you ultimately die because your cells stop being able to replicate, translate into different proteins. Okay. So why show you that? Because legitimately, if structure is important, unravel all this stuff, break it down into its individual amino acids, and now ask the question that we could answer in Chem 2. Like, what is the actual three-dimensional geometry at each of these individual central carbons or nitrogens? Okay, so let's do that. What is the electron pair geometry for this nitrogen?
Trigonal.
It is trigonal planar. However, if there is a lone pair of electrons there, what would that end up being? There is a lone pair there.
Trigonal pyramid.
That's trigonal pyramidal. So it looks like we have 4 different regions of electron density. 3 of those are bonding, so the molecular geometry is trigonal pyramidal. So that does get us back to one of our basic fundamental shapes, right? This guy, tetrahedral. Remove one of those, you get a trigonal pyramidal. So that's what it looks like here to begin with initially. What about this carbon? What's the molecular geometry there? That's tetrahedral. So we have 1, 2, 3, 4 regions, all 4 are bonding. What about this one? This one?
Radial planar.
Good. So 1, 2, 3 regions, all 3 are bonding. And then what about this oxygen here?
Linear.
It could be.
Bend.
Yeah, there you go. So it has 4 regions, 1, 2, 3, 4. And there's 2 of those that are bonding, that's bent. So if you're looking at that table, that short table on your introduction to Lewis dot structures, what is that, page 2? Where it just says the number of regions, the number of bonds, the number of lone pairs, what's the name? That's what you're doing here, is just kind of trying to piece that all together. Now, legitimately, why does that matter? excuse me, what if you say, I don't know, let's just make that another, it's not, but let's make this another amino acid. There's something called steric hindrance, the ability of this molecule in 3 dimensions to be able to approach and get into a certain space. Like, is it easy to get into here, or does it have to come out to the outside and bind? So there's a couple things that affect a rate of reaction. One of those would be how frequently do you collide. These two have to come together. If you come together once a second, you will not see any chemical reaction. If you come together 1 trillion times a second, now you will see reactions start occurring. So the frequency is impacted by the energy. The greater the energy, the faster you move, the more frequent the collision will be. And if you have a lot of energy, it gives you the ability to overcome the activation energy requirement for a reaction to occur, right? Because every reaction needs some amount to get that process started. So if that's 2 or 3 of the possible ones, the other one is the geometric arrangement. If it comes in like this, it may not bind unless it comes in like this. And if it's distorted slightly, we still don't have a chemical reaction. So that's why it's important to have lots of trillions of interactions a second, is so you get the right orientation. So in 3 dimensions, if this is now, I'm just going to make this up so I can hold them all in one hand. Let's say that is the molecule, the molecular shape of the amino acid, right? Where's that guy going to come? Like, how's he actually going to get into there? You can't push that atom away. It's not. It's stabilized by the interaction of that bond, so it's not like you can just brute force into there. But in order for chemical reactions to occur, in essence, if I'm treating this as the enzyme, so this is the substrate, or this is the enzyme, and this is the locking mechanism, and this is the key. If it comes into there, there's going to be a collapse of that structure. It puts strain on maybe one of these bonds. That bond ultimately ends up breaking. Good night. Ends up breaking, right? And when it does so, it releases that tension, releases the substrate, and now you have a totally changed molecule. So that's biological systems, right? You can see how that 3-dimensional shape totally impacts the ability to get into there. And that's a good thing. You don't want this, which might be Tylenol, coming into your eye cells, right? If that wasn't sterically hindered, then what would Tylenol do to your vision? That would be a bad thing if it starts conformationally changing your eye cells altogether. So that's kind of the big picture of why we care about Lewis dot structures, and the truest sense of it is because it totally dictates the biology or the biochemistry, the physiology of your life and all organism life, plants, amoebas, single-celled organisms, etc. Anything that has atoms in it, it affects. Okay, so if you can take big chains and recognize the molecular geometries at those positions, that's sufficient for us. Okay, so just kind of what we were doing there. All right, and then resonance. Let's say a little bit more about resonance, and let's also touch on formal charge here as well. How do I know if some molecule has resonance or not? What has to be true about that molecule?
It's got to be the same type, and it has to have a double or triple.
Okay, so it has to have at least a double or triple bond, check. And then that double bond or triple bond has to be bonded to the same type of atom somewhere else. So if this was a double bond here, and let's just go ahead and make this up for a second. If you had that, would you have resonance? You have double bonds, which is check, and you have identical atoms, that's check. So can you switch that double bond around anywhere? No? Yeah, you can't. So part of that kind of underlying thought is one of those bonding atoms that is identical needs to not have a double or a triple bond, right? If this was a double bond, or I know this doesn't exist, but let's make this up for a second. Would you have resonance then? What do you think? That a possibility? Yeah? Yeah, it is, because this is triple, that's double. There's different bond character. This bond character could go here, and the triple bond can now move down there to 2 different identical oxygen atoms. So that's still a possibility. However, very unlikely, right? That a triple bond is going to switch places with a double bond, because they're both relatively pretty stable. All right, let's go back to phosphate. Eventually, we would derive. Actually, let me do this. When you are doing your Lewis dot structure, initially you would have gotten this one to begin with. All right, Valence electrons for oxygen. Oxygen has 6 valence electrons, so we should have a total of 6 times 4, that's 24, plus phosphorus, which is how many valence electrons? So we have 24 for oxygen. How many for phosphorus? Valence electrons on the periodic table? 5. And then if this is the phosphate ion, these 3 additional electrons go in here as well, right? So we should have a total of 32 showing. So 8, 8, 8, and 8 makes a total of 32. Check for an octet rule. The 8 oxygens or 8 electrons around oxygen, 2, 4, 6, 8 around phosphorus. That satisfies the octet. Arguably, this would be very, very accurate. It doesn't violate anything that you've learned about Lewis dot structures. The hard part of this, and maybe the questionable side, is if you go to the internet, they would say this, a lot of people would say that's right, and it is wrong. And it's wrong because those that are trying to say it's right, arguably, are trying to understand like general chemistry. You guys at Chem 2 need to use formal charge to try and distinguish whether this is the correct structure or not. So let's talk about formal charge. There is a slight calculation here, and by slight I mean more straightforward. Formal charge is equal to the number of valence electrons for an atom minus the number of bonds and minus the number of electrons in a lone pair.
Is that in all the lone pairs or just one lone pair?
Only for the atom you're looking at. Yeah. So I'll show you an example. So let's calculate the formal charge of this phosphorus atom. So I'll say the formal charge of phosphorus. Okay. The number of valence electrons are 5. The number of bonds on the phosphorus atom, 1, 2, 3, 4, right? Minus the number of lone pairs on the phosphorus atom, right? Because we're just talking about phosphorus. So there are no lone pairs around the phosphorus atom. So that's a positive 1 charge. Positive 1 formal charge. Now, what is a formal charge? When you're looking at formal charges in oxidation states, formal charges do not consider electronegativity values. And that's not okay. Electronegativity, remember, is a defined empirical trend that says the desire of an atom for an electron. So how much does that atom want a particular electron? That is what formal charge is ultimately not telling you about. It's an overestimation of what electronegativity is. Actually, there's no consideration, so that's not it. Oxidation state is the overestimation of that. So for example, we could use something like calcium. We know that calcium will form the 2+ ion because it's a metal, it's in column 2A. But not once did we say, oh, what is the tendency of calcium actually empirically, based on its ionization energies and electron affinities, will it actually easily, readily lose 2 electrons? That would be a conversation about electronegativity. So we actually overestimate the fact that calcium will completely lose 2 electrons when sometimes it may not lose 2. It may just partially distribute its electronic character somewhere else. So I do have a question that legitimately asks you this for tomorrow. It says, does formal charge overestimate, not consider it indefinitely? Like, what's the aspect there? You legitimately just say formal charge doesn't consider in oxidation states overestimate electronegativity values. So you have to use both of these here in addition to everything else we're doing at this level. So what does formal charge say? Formal charge just says which one of the possible structures that you draw for phosphate are contributing to the overall structure more often. So for example, we could actually develop a structure like this where we have, this is the real phosphate. When I say real, this is the one that contributes the most to the overall structure. Who was it the other day? Maybe it was someone we were talking about, Jason, I think, maybe. I don't remember. Maybe Gloria, I don't know, my memory's vague. But at some point somebody asked, could this structure be different? Was it the carbon dioxide yesterday? Maybe that's what it was, yeah. And we just got to a point where, like, do you put a single bond there? Do you put a double bond there? Is that a triple bond? Like, what are the possibilities? That's what we're trying to get at. Yes, all of them exist, but what extent? Which one is the most favorable 95% of the time? All of them contribute, but to what degree, right? Okay, that's what formal charge is trying to do. Notice here we get the same thing, 8, 8, 8, and 8. That gets us our 32 valence electrons. So octet, 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 2, 4, 6, 8, 10 around phosphorus. Is that okay to violate the octet rule for phosphorus in row 3 of the periodic table? Is that okay? Yeah, because we're moving some of those 3s or 3p electrons to the 3d. The short version is this is a possibility, so is this. So who's right? Who contributes more overall? And then even then, you now have a resonance structure that you have to deal with. So now these are all single bonds, where that single bond here, double bond here, and you could keep going. So now you not only have a different structure altogether, you could use resonance as well and extrapolate that out. So formal charge is going to give us the ability to be like, which one's better? Okay, there are two things you consider with formal charge. You want no formal charge. So you want to minimize your formal charge altogether. And by minimize, I legitimately mean go for the value of 0. So formal charge equal to 0. On every atom possible. Why? That's a much more stable atom. Okay. If you do have to have a formal charge, then the negative formal charge preferably will go on the more electronegative atom. So negative formal charge prefers the more electronegative atom. Okay. All right. So who's more electronegative, phosphorus or oxygen? Who wants the electron more? What do you think? Further up and to the right means greater electronegativity. So oxygen wants the electron more. So if we have to have a negative charge, we want to put that on one of the oxygens. We do not want that on phosphorus. That's what this second statement means. Notice that this first one is not already being achieved. We're trying to get this to be 0, not to be any other number. So it can be positive, 0, or negative numbers. All right, let's do the formal charge here on this oxygen. So the formal charge here, there are 6 valence electrons for oxygen based on its position on the periodic table. The number of bonds, that's 1 bond. And then the number of electrons in a lone pair, 1, 2, 3, 4, 5, 6, right? So overall our formal charge is -1. Not good, right? Not good. Is this okay though? Do we put a negative charge on the greater electronegative atom? Yes, that's okay. What's the formal charge here, and here, and here? Okay, so -1, -1, -1. All right, and I'll put a +1 here for the phosphorus. Whatever the formal charges are, they still have to add up to the overall charge on the compound. So did we do that? Yeah? 1, 2, 3, 4 negatives plus 1 positive gives us a -3 overall. So that's okay. This is one possibility. Is it better than this one though? What's the formal charge here? Here and here. Okay. What about here? Yep. So no charge. So 6 minus 1, 2, 3, 4, 5, 6. Formal charge here? Also 0. -1, -1, -1 add up to be -3. The negative charges are on the atoms that desire them more, and we've minimized the number of formal charges we have compared to this structure. We have 1, 2, 3, 4, 5 formal charges, and here we only have 3. So by default, this one looks to be contributing better to the overall structure of phosphate than this one does, because there are more formal charges than this one. Does that make sense? So by default, what about here? Go ahead, what would this be? I've left out all the electrons, but you have enough. 0? What would be the next resonance structure? The same thing, right? And then the last resonance structure? It's the same thing. Okay. So now the question legitimately becomes, which of these resonance structures contribute more to the overall structure, and it's equal. We know that this one has to contribute the less to the overall structure of phosphate, and these structures all contribute to a greater extent of the overall structure of phosphate. And if we say these do contribute to the overall structure to a greater extent, then we collapse them together and we draw one resonance hybrid structure. So remember this from yesterday. Each image up here has at least one single bond, has at least two lone pairs around each oxygen atom. And then we said there's some bond character here that's being divided between those. So how much of a bond is this? 1 1/4, right? And that's how we got to that image yesterday. So legitimately, this is what phosphate looks like. If you're going to empirically say, what does the data show? 1 1/4 bond character. At any given moment, you could take any one of these images and compare it to this overall structure, and it still says this is better. This is better. Let's just do some quick formal charge calculations just for practice here. SO4, eventually you'd get here as one possible structure. For the rest of the year, you guys do not need to draw all the electrons in around there. You can just shorthand that to just be like this. And then we as a class will assume there's enough electrons around the bonding atoms to stabilize them to make a noble gas configuration. So 8 electrons ultimately. What's another possible structure? So if that's one possibility. Say that again, sorry. Okay, that's true. So do a little bit of resonance is what you're saying, right? So we have something like, what if we kept that one? That's one possibility, right? Another possibility would be something like that, right? Help me out. I'm losing it, falling apart. We rotate down, rotate over, keep that one the same, rotate down. Oh my gosh. Here, there, right? Yeah, okay. And then maybe another option or so. But in general, are all of these going to have the same formal charges? Yes. Right? Because you still have the same number of double bonds, you still have the same number of single bonds. So if we do it once, it's the same everywhere else. Formal charge here. For oxygen. 0. 6 valence electrons minus 1, 2, 3, 4, 5, 6 things. Here.
-1, -1, 0.
Good. So overall, is sulfate supposed to be a -2 charge? How do you know that based on the periodic table? Just looking at the periodic table.
Sulfate.
Yeah. So sulfur is in the area of the periodic table where you do O4 for the 8 form, right? And then it's 2 positions away from a noble gas, and you have to go to the right, so gain electrons. So what you've been memorizing in Gen Chem and Honors Chem 1 actually has real implications based on formal charges. Isn't that kind of cool to finally be like, sulfate, that's why it is what it is. No, is it not? So
Okay, to be fair, the last time I took chemistry was in sophomore year.
Yeah.
And then half the year got cut off.
That's fair.
And then once we got cut off, we had a substitute.
Yeah.
So that whole half of the year we didn't learn it.
Yeah, I just think it's cool that we just tell you to learn things, and then we're like, oh, someday you might learn why. Now you're learning the why. It's awesome. It's so cool. All right. What about if these are all the same? Is there another structure we could draw that's different from these?
Triple bond?
We could. Would that violate? So like onto an oxygen? Would that violate oxygen? So 2, 4, 6, 8. No. What would we? So let's check our number of electrons here. How many total pairs of electrons should we have around? Or for the entire structure. So oxygen has 6, sulfur has 6. 6 times 5.
30.
Okay, we need 30. Valence electrons. 8, 8, and 8 makes 24. Plus 8.
33.
Okay, so something would have to change. What might we change? So we have too many electrons here. So should we take some off of here? No, we can't just take those off, that makes that unstable. Can we take those and move them here? We can, so double bond, but then did that change the total number that we had? No, so we actually have to get rid of some. Where could we get rid of some at? Probably the thing that we tried to change in the first place. And now as, this is a -1, -1, -1 formal charge. What's the formal charge here? 6 minus 3. Right? What has to be, question, what has to be the formal charge of sulfur if this is sulfate? Because -1s cancel out with the +3. So let's double check. Sulfur is 6 minus 1, 2, 3, 4, 5, 6. It's like, wait, what? It's like, so this structure produces a 0 charge overall, you know what I mean? Right? So this would say that sulfate has no charge. So that is a possibility, but we could rationalize why it wouldn't work, fair? Because it doesn't give us a -2 charge overall. So what's another one? What else could we do? Single bond, I like it. Simple. But in regards to that, it's not a bad idea, especially with oxygen. Hopefully you can pick up that pattern at some point, that anytime you have oxygen, you need 8 electrons. It's easy to double bond oxygen and leave it with 8. You can move the pair of electrons out here, right? Release that double bond, and it looks just like what you had to begin with. So moving those electrons is easier than other atoms. How many total electrons are shown? 1, 2, 3, 4 times 8. Right?
Yeah.
Right?
Yeah.
Right? Okay.
Yeah.
All right, so 6 times 1, 2, 3, 4, 5, we're supposed to have 30, except for if this is sulfate, then this gives us our 30 electrons here, and then we add 2 more, so that gives us our 32.
Yeah.
So we're okay.
Wait, so could the other one?
Yeah, I think we forgot to add the 2. You're right. I think we forgot. But not the overall structure still violates the fact that it didn't have a -2. It still came out to be 0, but we had the correct number of electrons there. But the right number of electrons. What's that?
But then we took them away. So if we
Just leave them there. Yeah, and that would have been what oxygen would have been triple bonded. So the formal charge there would have been +1, right? And then that would have given us a +1 overall. So
it
this,
still would have been different.
yeah, still would have been +1. Yeah. Okay, and then here, what about the formal charge on these oxygens? -1. Okay, what about here? 6 minus 1, 2, 3, 4.
2.
Is that a -2 overall?
Yeah.
Okay, so that's a possibility. Which one's better, this one or this one? Which one contributes more? Why? It has more zeros. They all have negatives on the right spots. The positive is with the lesser electronegative atom. That's fine, there's no problems there. But this has a lot of formal charges. It has 5 overall, and that only has 2. So this is better. And then you do resonance, and then you make a resonance hybrid structure on those. Yeah? Okay, all right, let's practice unit partners, resonance, formal charges.
I don't know how to do CO.
Let's do this one. And let's do it together. All right, grab one of these.
I can do it all my time. And then it'd be super.
We can.
So
Yeah, so we'll
it's
do
good for. I don't remember how to do CO.
Sorry.
No.
I was making something for you. Yeah, come grab one of these.
So,
And then we'll dig in a whiteboard, we'll dig them out.